To the third video in our series on LiDAR visualization using free and open source software. I'm Kevin, and today we are going to cover rasterization of LiDAR. So for this, we finally get to use QGIS, which is really the main player in all this, to process our LiDAR data into a usable format for visualization. So we'll go ahead and open QGIS. Like I said, I'm using the long-term release, the latest long-term release, that's PrisRun. Got some messages there. All right, this is QGIS. So the first thing we need to do is start a new project. We can press this blank page up here for new project. So we've now started a new project. And important here at the start is to, as I stated before, was to choose a coordinate reference system. In this case, I've chosen FSIG 6344, that's UTM zone 15 north, because it matches the data that I've already downloaded. It matches my point cloud data, and it's a good choice for working at this scale in this area in general. So I don't see any reason to change that. So we're going to leave this coordinate reference system. If you did need to change it, you could use the search bar up here to find it, or select from your list of recently used coordinate reference systems. Then you click the apply button, and your coordinate reference system would be set. So the first step, we're going to save our project. So we'll go up to Project, Save As. I'm going to save it in the same folder where I've been storing my data. And just to be consistent, we're going to call this YouTube tutorial. Save. So now we have a project file. So what we want to create from our LiDAR point cloud is a raster. And a raster is basically a picture. I've heard people refer to these as LiDAR pictures online, and that's not a terrible way to describe it. What we're creating is a picture. Specifically, we're going to make a GeoTIFF. Now, a TIFF is just a picture file format. A GeoTIFF is just a picture that is placed in somewhere on the Earth in a coordinate reference system. So to do this, we're going to use probably my favorite plugin. I spoke about it earlier, about Open LiDAR Toolbox. This is really great. It even has a one-step processing option, which does everything with basically one, you just set it up one time, it runs everything. It has all these individual options below to do the individual parts of this process. And so I really like this. It just takes a lot of the steps out, and it creates a really good model. So this is going to create a hybrid model based on how dense our ground points are. So I will choose a resolution. A resolution is just the size of my pixel for my LiDAR picture. In general, with USGS, a pretty good resolution to choose is a 0.5 meter. Just because I tend to have at least 1 point per 0.5 meter. But if you wanted to check and have confidence in what you've chosen, you can create this DFM confidence map, and it'll show you the areas where your ground point density maybe isn't as great. Areas that it is good, it'll choose the best method of interpolation when creating this raster, whether to use inverse distance weighted or triangulated irregular network. I really like that it uses this hybrid model. I feel like it catches features, it models features better than doing one or the other. And so this is my method that I use. So we're going to choose one-step processing. And we've got to fill out all these parameters. And then we're going to click Run, and we'll get a result. So for this input LAS-LAZ file, we are going to select from our LiDAR folder this merged classified that we created earlier. These were individual tiles that were not classified. This has been merged together and classified, so it contains only ground points. So we're going to select that. In order to skip some of the extra steps that go along with classifying data, is the input file is already classified. Ours is classified, so we can click this. Remove low noise. If your data suffers from low noise, then you can click this option and it will remove that. There's some important information here on the side about what you need, what are the requirements for your data that goes into this, and then what it's going to produce. The most important thing to take from this over here, I'm not sure where it says it, but your coordinate reference system has to be in meter. Here it is. Tool will not work correctly with data in feet, kilometers, centimeters, etc. It must be in meters. It uses some distance properties, and so say this was in feet and I enter 1/2 as my resolution, it's going to think that that's in meters, which would be 6 inches instead of a 1/2 meter, which is a huge difference. So very important that your point cloud is in a coordinate reference system that uses meters as your unit of measure. For source file coordinate system, I'm going to leave this. This is the correct coordinate system that my data was in that we checked in Cloud Compare earlier. And cell size is 1/2. I like that. 1/2 meter works good. These down here are your products. So DFM, digital feature model, that's synonymous with digital elevation model, which is the term I use. And that's just a bare ground representation of the topography. So all the trees, all the buildings, all the roads, all the railroads, all the power lines, all that has been removed. And then we have all these other visualizations. I don't necessarily need ground point density. I'll leave that in today. It might take a little longer to run, but you can see what that is. Low vegetation density, definitely don't need that. Confidence map, that's fine. These visualizations are really the main product we're going to look at, as well as the DFM. This visualization hillshade, I'm actually going to uncheck this box. I know our final product we're shooting for here mainly is a hillshade. That's what we're going to use to look for features. But this hillshade it's only going to be one directional. We won't be able to play with the angle of the sun or its direction. And I just really don't find it that useful. So I'm going to uncheck that box as well. And then we'll press run. Now be warned, this step may take a while depending on your computer setup. We'll run this in real time. You guys can wait it out with me. And while this is running, I'll cover something I forgot in my previous video. One of the other things I like to do in Cloud Compare is I can view my point cloud. I'll zoom way in, and you'll notice you have a small scale bar at the bottom right-hand corner of your screen. I'll zoom way in until that scale bar is 1, which is 1 meter, and kind of compare it to the points that are represented on the ground. And since my kind of target resolution here usually is about a 1/2 meter, that allows me to look and see, do I have a point in general every 1/2 meter, or is it way denser than that? You know, every 1/4 meter, or even more? Could I process this at a higher resolution? Or is it some older USGS data, it's really not as good, and I need to back that off to 1 meter? If you have your resolution set too fine, the program will have to interpolate between points much more intensively. It'll take a really long time for your computer to run it. As well as it's just made up data. It's not good. It's not good. So that's just a good way to check that. Okay, so we're off and running. It has loaded it. You'll see lots of red warnings. That's okay. Red warnings are fine. It's still running. If you're doing a really big data set or big for your computer, I usually have Task Manager running in the back in case I need to kill it. But we are making progress. I guess while this is running, I might as well talk about some of the point cloud tools that are built into QGIS. I talked about earlier, if your coordinate reference system or your point cloud is in a non-meter unit of measure, so like feet, you'll need to reproject it. So you have the option here to choose reproject, and you can select that, select your point cloud file. You'll choose your source coordinate reference system, which we got from that line of data in Cloud Compare. And then you can reproject it to a coordinate reference system that's based on meters. What a projection is basically, we're representing 3D points on a round surface onto a flat surface. So a projection is how those points are projected onto this flat surface, which is your map, which is your visualization. Coordinate reference systems is a really involved topic, which I won't cover in any more detail today, other than to say that it's very important, and you should try to gain some amount of understanding of what exactly that means. It's still running. Lots of red warnings. That's okay. Error. That's okay. Thankfully, the author of this plugin has done all of the heavy lifting for us to make this a almost one-click option for processing LiDAR data. There were other ways to do this before, even to do this exact process before. But you can see all these steps that it's ticking through as it processes. So you can imagine running these one by one was a huge pain. All right. And it is complete. So we can close this out. You can see we have all of our data products over here. So one of the important things to remember about this, this little symbol right here, that means this is a temporary layer. So if you want to use this in the future, you need to save it permanently. So I'm just going to run through these first, and then I will save them after I conclude the video. Maybe I'll show you how to do one, but there's no reason to run through that on all of them. So the first visualization is this VAT. That's visualization for archaeological topography. This is the area we're kind of interested in here. There's a creek that runs through the valley here. And you can see there's quite a developed road network. Let me go back to Google Satellite. Let's add Google Satellite. I think I might have forgotten to do that at the beginning here. There it is at the bottom. So we'll drag that all the way up to the top. This is our layers panel. This is where all of our data is. You can see what layers you have on, what order they're in, and their properties. So this is Google Satellite. You can see here we've got a creek that comes through here, but it just looks like forest. There's nothing to see here from the aerial alone. But we uncheck that, and you see all this road network. It just jumps out at you very clearly. So we'll revisit that later. The second is the DFM, also known as the DEM. This is the default visualization that I guess I have enabled right now. I'd say the most common way this comes in would be as single band gray. As you can see, this just looks like a gray square. Not very useful. But if we go to Hillshade, this is the more traditional LiDAR picture, quote unquote, that you're probably used to seeing. And we'll visit this more in a future video on how to manipulate this to see features that we're looking for. This looks like this is our confidence. So red is low confidence, this kind of yellow color is medium confidence, blue is high confidence. So this just has to do with the density of ground points that we have. So as I zoom out, you can kind of see it's mostly blue. Yellow, this pale kind of straw yellow is okay. And then the red's mainly on the water. So that tells me that the half-meter resolution, it's probably okay. That's an appropriate resolution. I don't have any use for this layer after this point, so I'm going to go ahead and remove it. The next visualization is SVF, which is Sky View Factor. You can read up on all of these. The author of this one LiDAR toolbox has a nice academic paper talking about all of these visualizations and what exactly they are and how they're calculated. And it's a fairly heavy but interesting read. But these can all be useful later. The last is openness. This tends to make it look almost like a flat, it almost flattens the map, but really accentuates features like road networks, rivers, changes in topography. This last one, this is our ground point density. Also not particularly useful. I'm going to go ahead and delete that. I won't go into that today. Okay. And the last visualization is DME, or distance from mean elevation. This one's also extremely useful. You can see it almost has created a flat map as well. Really makes these changes pop though. I mean, these roads, these are like overgrown nothing trails, and they just really stick out. So this can be very, very helpful for visualizing. So I'm just going to go over, let's see here, do we have one more? That is the last one. All right, I'm going to go over, like I said, these are temporary layers. I'm going to go over how to save them, and then we'll conclude the video, and I'll save the rest off screen. Let's go to visualization, distance from mean elevation, and we want to save this, so we want to export. So we're going to save as, export save as. We're going to choose file name, and I'm going to put this under raster because this is a raster data set. So this is DME. GeoTIFF is a fine format to save this in, so we'll do save. Current layer extent should already be checked. That just means we're saving the entire layer. No need to change any of these other options. And we'll leave add save file to the map checked for now. Click OK. So it has now saved that file. So you notice this looks different. Why does this look different? This is the same as this. I just saved this. You notice the scale over here, the way it's styled is different. It doesn't change this on every layer, but I've noticed particularly for the DME, it doesn't save the style correctly. So you can see here it goes from -0.5 to 0.5. There's a really easy way to make this look exactly like this. And that is to right-click, Styles, Copy Style, right-click, Styles, Paste Style. There, now we've saved the style from this layer to that one. Super handy. You also see a question mark here. That is indicating that it doesn't know what the coordinate reference system for this layer is. That's probably my one gripe with this tool, is it doesn't necessarily code the well-known text for the coordinate reference system to the layers properly, but we can fix this easy enough. I know this is in 6344. I know that. So I click OK. So that has assigned it a coordinate reference system, but it doesn't always append that to the file. So the way to fix that, we're going to go up to our processing toolbox and we're going to search assign. This assign projection, this is for raster. Click it. Input layer is DME. That's the layer that we want to assign a projection to. And you can see here this invalid projection. Let me close this real quick. I'll right click on this and show properties. If we go to metadata, extent, coordinate reference system not set. Well, we just set it. It doesn't save it to the file. It just tells this project that that's what it is, but it's not actually modified this file anyway. So from layer, hey, that picked it up. Provider, not set. That's a problem. So we'll do cancel, assign projection, DME. We're going to select our project coordinate reference system and do run. This should go really fast. Boom, done. All right, this has now had the coordinate reference system assigned to the actual file. So if I were to copy this file and email it to someone, it would have that information appended to it. So we're going to follow the same process for the remaining layers off camera and save them to our raster file.